Spitzer Space Telescope, one of NASA's great observatories, was designed to reveal the universe in infrared light. NASA's Great Observatories program was a collection of 4 space telescopes that looked at the sky in different wavelengths, ranging from high-energy gamma rays to low-energy infrared light. Observing the sky in different wavelengths gives us insights into a wide variety of physical processes and objects in space that we could not study without such a large wavelength range. NASA's Great Observatory, collecting the highest energy light, is the Compton Gamma Ray Observatory. Compton is the first telescope on this list of 4. It carried a collection of 4 instruments which together could detect a broad range of high-energy radiation, called gamma rays. The mission provided insights into the basic structure of the universe and distribution of high-energy radiation. Compton has also helped us further understand black holes and supernovae. Compton was launched in 1991 and deorbited in 2000. It cost $617 million and was the second of the great observatories to go into space. Originally, gamma ray telescopes were created for detecting nuclear explosions, which emit gamma rays. However, they ended up finding these rays in space. The main purpose of Compton was to find out if these gamma ray bursts were in the Milky Way or if they were extragalactic. It found them all over the sky and proved that they are from outside our galaxy. Launched on July 23, 1999, the Chandra telescope differs from other space instruments in that it is designed to detect and analyze X-ray emissions from hot regions throughout the universe. X-rays have a lower energy than gamma rays, but higher energy and shorter wavelengths than ultraviolet light of visible light. X-ray telescopes are able to collect the photons from any given region of the sky. The information determined from the X-ray photons collected can then give scientists clues about the temperature, composition, and density of faraway objects in space. Chandra allows space scientists to study our galaxy clusters, matter surrounding black holes, recently exploding stars, superheated gas clouds, and much more. X-ray telescopes like Chandra are launched and placed in high altitudes into space due to the Earth's atmosphere as it absorbs most X-rays. The next great observatory, and probably the most well-known, is the Hubble Space Telescope. First conceived in the 1940s, it took decades of compromise and construction to complete the Hubble Space Telescope. It was launched into low Earth orbit in 1990. Though it was not the first telescope NASA launched, it is certainly one of the longest and most versatile of the fleet, still observing well into the 2020s. With a nearly 8-foot mirror, it is able to peer deep into space. Beside the mirror, it has many scientific instruments, including spectrographs and high-speed photometers, with which it observes the universe. Hubble can collect a wide range of photons, ultraviolet, visible, and near-infrared. The Hubble telescope is one of NASA's long-lasting missions, as well as one of the most successful. It has provided us with many stunning images that have led to groundbreaking discoveries and has played a key role in learning more about the expansion of the universe as well as its creation. Scientists have been able to observe and map all of the stages of evolution in a galaxy and how they form. Perhaps the most incredible part of the instrument is that the telescope and its images are accessible for anyone who wants to use the Hubble to study astronomy or deep space. Astronomers from all over the world are permitted to submit a proposal to use the telescope in hopes of getting a chance to utilize the telescope's technology to answer any astronomical questions they may have. And that brings us to the coolest of the great observatories, Spitzer Space Telescope. Spitzer was an infrared telescope used for viewing dust clouds, planets in our solar system, exoplanets, galaxies, and more. Spitzer was launched in 2003 and had a 2-part mission. During its cold mission, it was cooled down to negative 450 degrees Fahrenheit, but once it ran out of its supply of liquid helium, it started its warm mission, which is for observing near-Earth objects such as asteroids and comets that orbit the Sun near Earth's path. Spitzer's missions totaled to around 16 years, with 5.5 years being for its cold mission and 11.5 for its warm mission. Water vapor in Earth's atmosphere blocks infrared light, so infrared telescopes on Earth have to be at high altitudes and in dry environments to avoid as much water vapor as possible. Spitzer avoids this problem by being outside of the atmosphere altogether and orbiting the Sun behind the Earth. Besides having two missions, one cold and one warm, Spitzer is divided into two compartments, the spacecraft and the cryogenic telescope assembly. The spacecraft is the part that keeps Spitzer functioning. It is the warm part of the telescope and contains the solar panel assembly and the spacecraft bus. The spacecraft bus contains the warm electrical parts of the scientific instruments and the avionics, which point the telescope and communicate with Earth. This part needs to be near room temperature in order for the equipment to work. But that means it glows in the infrared, which would flood the telescope if not designed with great care. Thankfully, Spitzer was well designed. The cryogenic telescope assembly is the cool part of Spitzer. And when I mean cool, I mean cold, 5 Kelvin above absolute zero. It contains 4 parts: the telescope, the instrument chamber, the cryostat, and the outer shell. The outer shell is what keeps the telescope cool. It's painted silver and black. The silver side faces the sun. It reflects as much radiation as possible. The black side is pointing away from the sun and is painted black to radiate as much heat as infrared light into space as possible. The outer shell keeps heat from getting to the telescope. This allowed the liquid helium coolant to be saved for the instruments instead of being used to cool the telescope. The liquid helium is stored in the cryostat. This coolant was used to cool the instruments to an astonishing 1.4 Kelvin. Spitzer had 95 gallons of liquid helium. It lasted over 5 years, thanks to the amazing engineering that cooled the telescope in innovative ways. The instruments were kept in the multiple instrument chamber. This was the light, tight box, 3 feet 9 inches wide by less than 8 inches high. It kept all the extraneous light out so that only the light coming through the instruments came through. It had an aluminum baseplate connected directly to the cryostat. The telescope was 3 feet 9.5 inches, or 85 centimeters, and weighed less than 110 pounds. This is lightweight for a telescope. A common visible light telescope on Earth is a Schmidt-Cassegrain reflector. One example of how much telescopes weigh is a 14-inch Schmidt-Cassegrain that weighs 46 pounds. The Schmidt-Cassegrain telescope weighs 42% as much as the Spitzer telescope, but only has 17% of the area. Spitzer is so lightweight because it was made primarily of beryllium, a strong but extremely lightweight material.
The technology used on Spitzer is amazing and innovative, but the scientific discoveries that came from Spitzer are incredible. We'll start close to home. One of Spitzer's most remarkable discoveries is right here in our solar system. Spitzer discovered another ring around Saturn. This is Saturn's Phoebe ring, a distant structure only visible in infrared light, the very same kind of light which Spitzer detects. It is by far the largest and most distant Saturnian ring, so large that it would look twice the size of the Moon if it was visible from Earth, but also stretches very close to Saturn. Due to the planet's glare, this portion is hard to see. The Phoebe ring is made up of material that was shot off of the moon Phoebe after a variety of asteroid collisions. This material also strikes the moon's Iapetus and Hyperion. Moving further from Earth, but staying within our galaxy, is the next area of study for Spitzer: exoplanets. Exoplanets, planets orbiting other stars, are extremely difficult to detect and even harder to observe in any meaningful way. The glow of stars is incredibly overwhelming, and brighter stars will absorb planets in their glare. However, in slightly dimmer systems, it is possible to see the shadow of planets move across the face of their home star. This is one of the most common detection methods, and was used by Spitzer to detect planets in one of the most fascinating systems of all, TRAPPIST-1. The TRAPPIST-1 system has 7 planets, each of which has a similar size to Earth, and 3 of which are in a position suitable for liquid water, though no proof of such has yet been found. Larger telescopes, such as the James Webb Space Telescope, are needed to see signs of water. These 3 planets are located in the habitable zone, which is the distance from the star where the temperature is right for liquid water to exist on the surface. Each of these planets has strange and unique qualities. First is TRAPPIST-1b. Conditions are similar to our neighboring planet Venus, but arguably even worse. Stellar winds from TRAPPIST-1 tear at it, and temperatures are so high that it may be covered in lava. TRAPPIST-1c is quite similar, but a bit more tame. It may or may not actually have an atmosphere at all. Next is TRAPPIST-1d, the first of the planets in the habitable zone. Though dangerously close to the star, it may be habitable if it has certain climate conditions. The planet may either be a desolate wasteland, like the two before, or a hot yet survivable alien world. Then there's TRAPPIST-1e. It is well within the habitable zone of TRAPPIST-1 and would even function properly if it has an Earth-like atmosphere. However, beyond this, the planets are wastelands once again. TRAPPIST-1f and 1g are likely covered in snow and have frozen oceans, while TRAPPIST-1h could either match these conditions or have an atmosphere like the Saturnian moon Titan. Another interesting observation made by Spitzer is a heat map of an exoplanet's atmosphere. HD 189733b is a blue gas giant slightly larger than Jupiter, and Spitzer used its infrared emissions to measure its heat. This heat won't last long, however. The planet could be losing anywhere from 1,000 to 100,000 tons of its atmosphere per second. Its massive size means that this process will take a long time for it to fully disintegrate, but knowing this gas giant's inevitable fate is chilling nonetheless. Spitzer studied much more within our galaxy than just exoplanets. It also studied star formation, brown dwarfs, dying stars, and giant molecular clouds, but it didn't stop there. Looking beyond the Milky Way, Spitzer also studied other galaxies. There are three main sources of infrared light in galaxies: stars, dust, and gas clouds. Those all come together in star formation. Stars form from massive clouds of gas and dust which collapse. These clouds glow brightly in the infrared. Spitzer was good at discovering signs of star formation. Not only could Spitzer see signs of star formation in galaxies, but it was also good at observing black holes. Black holes release radiation in a wide range of wavelengths, from radio waves to X-rays. Sometimes, thick clouds of cosmic dust can block the visible and X-ray light from black holes, but since Spitzer can see through the dust and they also glow in infrared, it discovered several missing, active, supermassive black holes. Spitzer also had detectors sensitive enough to pick up the cumulative glow from galaxies too faint to be seen individually. This light is known as the cosmic infrared background. By studying this, astronomers can learn more about the history of star, galaxy, and dust formation in the early universe. But beyond star formation and black holes, Spitzer can also observe giant, distant galaxies. As the universe expands, the galaxies in the universe turn from ultraviolet and visible light to infrared. Because of this, the Hubble Space Telescope couldn't see these lost galaxies. Since Spitzer observes in the infrared, it was able to observe the old universe that is invisible in the visible wavelength range. In fact, Spitzer was able to detect light from galaxies released only a few 100 million years after the Big Bang. As you just learned, Spitzer made some astounding discoveries. Infrared technology is only becoming more advanced. The James Webb Space Telescope, NASA's latest infrared mission, is providing even clearer images and more data than the Spitzer telescope. In fact, the Spitzer Beyond mission started in 2016 when it ran out of coolant to locate targets for future missions, including Webb. As the world's most powerful space telescope, it is designed to further the work of other NASA telescopes, including investigating the TRAPPIST-1 system. Astronomers are excited for the future as infrared telescopes continue to reveal new planets, galaxies, and more. Throughout the years, we have grown and expanded our knowledge through the use of many tools. The great observatories are an important part of this growth that has allowed us to advance so much into our understanding of the universe around us. Spitzer, as the coolest of the great observatories, provided an excellent look into astronomical objects as diverse as Saturn's rings, exoplanets, and distant galaxies, setting a good foundation for high-resolution infrared astronomy.
I give up.
Hey, what's wrong, sport?
Hey, Stampy. It's this engineering class. I can't figure out how something like the Spitzer Space Telescope stays so cold in space.
Sounds like you've got a question for NASA. You should write to them.
I can email NASA?
Even better, you can mail them a real letter. Taking that extra time shows NASA you really care.
Sounds like a first-class idea, Stampy. Get it? First class.
Yeah, I never heard that one before. Whoa! Let's get this letter to NASA. That'll do the trick. Special delivery!
Hey, Stampy, got another letter for me?
You know it.
How does Spitzer stay cool? Great question. You see, Stampy, Spitzer is an infrared telescope. Infrared light comes from anything that's warm, even from things that are really, really cold and only a tiny bit warm.
Wow!
To detect infrared light from really cold space objects, Spitzer's instruments need to be even colder than those objects. Ideally, just a few degrees above absolute zero.
0 is a number.
I think this hologram and handwritten note should explain it pretty well.
I don't think you can reuse stamps. Okay, let's do this. Special delivery.
Whoa! Talk about airmail!
Yeah.
So, Spitzer was launched into space with liquid helium coolant to keep its instruments cold. But to help them stay cold longer, Spitzer was sent into an Earth-trailing orbit. This means it orbits the sun behind the Earth, far from the Earth's warmth.
I bet that's a crazy temperature difference, huh, Stampy?
I'm just a stamp.
In addition, the telescope's solar panels were mounted on a large structure to basically provide shade from the sun's light and heat. These passive cooling techniques meant Spitzer could make a small amount of liquid helium coolant go a lot farther. And launching with less coolant saved NASA over $1 billion. Wow, this is really helpful.
That's engineering for you. Well, thanks for watching.
But I have another question.
Uh-oh.
How come Spitzer is all black and silver?
Is that a clever engineering thing too?
Or is that just a funky design choice?
New stamps are surprisingly inexpensive. I can't feel my brain. Special me bumblebee!
Spitzer is black and silver because it's both clever and funky.
Yeah.
You see, silver reflects light, while black absorbs and re-radiates light more than any other color. Together, black and silver help redirect the flow of heat around the telescope.
You're saying science.
I have another hologram that depicts this exact point.
That seems implausible. Oh boy. I'm a choo-choo train!
Chicka chicka choo choo.
So, solar panels capture the sun's energy to power the telescope.
Scopy-dopey-doo!
But the rest of that side is silver to reflect the extra light away. Now some light is absorbed and converted to heat, so there's a black strip here to help radiate it back into space.
Ooh.
Heat that gets through would be re-emitted as light over here, hitting the silver side of the telescope's barrel and bouncing off. And whatever light does get absorbed is pretty much immediately conducted to the black side of the barrel and radiated safely away. The end result is, those black and silver colors keep the telescope's sensitive instruments even colder. Wow, sounds like those engineers really thought about this.
I'm Stampy.
And you really addressed my question. Thanks, NASA engineering person.
You're welcome, letter writer.
See you next time.
Time.
should send a thank you letter.
Ah!